to those of you who've stayed till the end. I'm tempted to offer a vote, talk or bar. But I'm afraid the bar's closed. Oh my God. All right. I should tell you guys, most of you know, those of you who know me know that I'm not a coder and I'm not a data scientist. Everything I know about Spark computing I learned tonight. And the stuff about the money and the anonymous fund was kind of cool, kind of interesting. But it's been really great. You might ask, well, why did they ask you to close this session? And that would be a good question. One hypothesis would be that they needed an old guy to sort of lend dignity to the proceedings. And there's a lot of empirical evidence here for that. I've looked vainly all evening for someone older than I am, and I haven't succeeded yet. So another kinder hypothesis would be that my lab over the years has actually been a place where new data analysis techniques and to some extent data science has met neuroscience, and I just maybe offer some historical perspective here of sort of what that has meant historically to the field and what I think it can mean in the future. So I'm going to run with that one. I would like to say just at the beginning that I didn't come into neuroscience deeply knowledgeable about the value of modeling and sophisticated data analytics. We just kind of stumbled into it in the lab, and it really was a matter of stumbling around in the dark, realizing we were stumbling around in the dark with our electrodes deep in the brain and this monkey doing things, and looking for some light anywhere we could find the light, and it came largely through quantitative modeling and statistical techniques that helped us to interpret what we were seeing electrophysiologically. And just to kind of illustrate this for you, I want to take you back to the late 1980s. This is a sort of classic paper that we published in '92, but in the 80s, we were sort of the first lab to have electrodes in the brain and actually record from visual cortex neurons while an animal was doing discriminations, a peri-threshold psychophysical discrimination, emotion discrimination in this case. And we published these I still think, so many years later, remarkable findings that showed that, the psychophysical performance of an animal in terms of percent correct as a function of the strength of emotion stimulus. The psychophysical performance that's shown here in these open curves can be characterized by a threshold where the animal gets 80% correct or so. But the performance of single neurons in the monkey visual cortex is damn near as good as the psychophysical subject. Sometimes the neurons can be worse, but sometimes the neurons can actually be better than the monkey's psychophysical performance. And this was a fairly startling discovery at the time. And, the psychophysics here, people have been doing that for ages. A lot of our novel contributions came in characterizing these so-called neurometric functions. And I just want to tell you an amusing story here and show you some figures that I had my admin scan out of our old lab notebooks recently that have never before appeared in public. This is published data from the paper, and the way we characterize neural performance, or what you can read this as the ability of an ideal observer to identify the direction of motion in a stimulus as a function of the signal-to-noise ratio of the motion stimulus. And this discriminability power of the single neuron depends on how well the neuron responds to a preferred direction stimulus versus a null direction stimulus. And here, where these distributions of responses are essentially non-overlapping, the ideal observer, based on the single neuron, would do extremely well. And here, where they're completely overlapping, you would do poorly. And what we did was characterize these with these ROC curves based in signal detection theory. And this is an analysis that just measures the degree of overlap of these things. So, what you can do then is just integrate the area under these ROC curves, which turns into the percent correct performance of the ideal observer. So if this is a unit square here, this ROC curve comes from this pair of distributions. The integral is around 0.5, which is 50% correct, and so on up to 100% correct. And by the time we published this paper in 1992, we had computer programs to do these these kinds of things. But at the time Ken Britton and I first started making these measurements, we had the only computer program we had in the lab was one that dumped out the total number of spikes on a single trial. And so what we had to do was actually build these distributions. We built them by hand, and we calculated these ROC curves by hand on graph paper. And this was one of the very first ROC curves that we pulled out of MT. And we literally did this by hand, and when we got the ROC curves, we could tell there was an orderly relationship here with the neuron. We were very excited to see the neurometric function, but we didn't have a program to integrate the area under here. So what we did, we took scissors, we Xeroxed this, we took scissors, and we cut out each ROC curve, and we weighed them on a Mettler scale. And out of that came the very first neurometric function out of the lab. So we were computational in the sense that we understood integration, right? I mean, and this is literally one of the very first comparisons of neurometric and psychometric functions. Now, looking at single neurons like this led us to think about populations, right? If single neurons are so damn good compared to the monkey, I mean, why do you have millions of neurons? How do you pool them? What limits the fidelity of neural representations? And Mike Shadlin came into the lab about that time, and he started doing, these simulations. And I had never been involved in simulations at all, but Mike convinced me how valuable these things were because we were about to write a discussion section and just say there's enough information in MT to support the animal's performance. Well, duh, right? And what Mike showed us is that we could actually do simulations and calculate the performance of a neural population as a function of the size of the neural population. And we could actually introduce levels of correlated activity into the neural population and understand quantitatively how different levels of correlated activity limit the benefits you can get from pooling. So we could actually write a discussion section that was quantitative and made certain kinds of predictions and highlighted the need for these kinds of measurements. What is the correlated activity inside a sensory pool? And it inspired better experiments. And this kind of data analytics and modeling and simulations, it was a source of light for us at the time. And this is taught now many times in undergraduate computational neuroscience classes, and many of you are saying, is this why this lab got so famous? But I can assure you that in 1994, this was novel and cutting edge enough to be published in Nature. And Udi Zohari actually made the measurements. So this is an example of how far we've come in the time since then, right? But I think that this experience that we went through in the lab actually getting some light, looking for it, and how do we interpret this stuff, and how do we start establishing principles underlying population coding became a paradigm for us and many other labs over the years that you guys are taking to unscaled heights now. So this is sort of my computational firmament, my conception of this computational neuroscience thing that I saw grow over the course of about 30 years. And we have all these measurements that we make in the lab, from synaptic potentials all the way up to learning and network kinds of architecture, the kinds of connectomic things you've seen this evening. And we're looking for light for how to interpret these things, and we have sources. And I view this computational firmament as having sort of three subsets. One is high-level statistics, signal processing techniques, basic data analytics. Another being models, neural network models, other kinds of models and simulations that we learn to and use profitably. And then another one, theory. So Deep's brother, Surya, my colleague at Stanford, who would be loath to sit down and build and run a network himself, but he'd love to write down an equation, a set of equations that describe the family of networks that could, in principle, solve a particular problem, right? That's kind of... Oh, are you back there? Surya's back there. Okay. I didn't know you'd come in, Surya. You're out. All right. I'm busted. Totally busted. All right. I understand that these are overlapping. All right.
He's not my real brother.
All right. Exactly when did I lose control of this talk? So This is something that we actually, most of you know that I was co-chair of the brain planning committee for the Obama administration. And this is actually a quote out of the section on theory and what we call theory, modeling, computation, and statistics, or TMCS. And this is kind of radical. It looks it's beguilingly simple, but it's pretty radical. The overarching goal of theory, modeling, computation, and stats and neuroscience is to create an understanding of how the brain works, how information is encoded and processed by the dynamic activity of specific neural circuits, and how neural coding and processing lead to perception, emotion, cognition, and behavior. Now, I can tell you I had dinner with a guest speaker at Stanford 2 or 3 years ago with a colleague of mine, a genetics-oriented colleague who won the Nobel Prize in chemistry about 2 years ago, which for most of you narrows that right down. And at the beginning of this dinner, he was, I guess, making conversation with me, a systems neuroscientist, and he said, Bill, there's never been a really fundamental discovery in neuroscience, and there's unlikely to ever be, that doesn't involve genetics. And I paused for a few seconds and I said, Tom, that's the most ridiculous thing I've heard in the last 6 months. And the conversation went downhill from there for the rest of dinner. And to my colleague, this is a radical statement. It's genetics, it's patch clamps, it's ion channels where real understanding comes from. But I think it comes at the level of theory. And I think that neuroscience will only mature to the extent that we discover basic principles of neural coding and computation that connect diverse data sets and predict the results of new experiments and new manipulations of brain and behavior. Identifying deep fundamental principles and organizing data is so critical to our maturity as a field. And I remember some of you were at the NSF, that chaotic meeting back in May of 2013 where in the wake of the excitement of the Obama announcement, 130 or so neuroscientists came together and each stood up and said for 2 minutes what they thought the future of the field was and where it should go. And there was all of this enthusiasm. It was total chaos. Robert Laughlin, theoretical physicist from Stanford, won the Nobel Prize for superconductivity theory, stood up to give a plenary talk, and he told us to rein in our enthusiasm and be careful what you wish for with all these super tools and new, fantastic data sets. He said, be careful what you wish for. The danger is that 10 years from now, you'll have disks and disks and disks full of data, and you'll only be 10 years older. That's kind of the fear, right? So I think we have this sort of polar dialectic that we need to move between. So we have these absolutely astounding new tools. This is the light sheet microscope that Phil Keller, from courtesy of Phil Keller and Matt Staley from Genelia, and Misha Arens showed us spectacular results that are obtained from this setup today. And we can get those data sets, but yet to some extent we're going to be data rich, and we have to do some thinking about this stuff, right? And the thinking comes from trying to really model these things and really deeply understand what they mean and relate them back to integrated data sets. And a big thing that we have to think about is what scale of detail do we really need the information? Where can we course grain across details? If we have to know every detail, we're hosed, right? And where is it legitimate to cross scales and make generalizations and identify principles at a higher scale? But where are the details really important? And if we miss those details, we're going to go deeply and badly wrong. I think that question is up for grabs in a lot of areas of neuroscience right now. And it's going to be, it's going to take us a good decade to sort that out. But I think, if it gets sorted out, when it gets sorted out, the people in this room, people like you, are going to be the ones who sort it out. So for the future, if I were, a young person in your shoes today, I'd be thinking about 3 things: funding and jobs, right? Funding, academic jobs, or in light of some of the talks we've heard today, private sector jobs. Funding, I'm cautiously optimistic about. I think the NIH Brain Initiatives has the potential to generate quite a bit of funding for the kind of integrated science we've seen talked about tonight that flows back and forth between the beautiful new measurements we're capable of and deep understanding of them. The Simons Foundation has just started this collaboration on the global brain that has funded quite a few collaborations of the kind we've seen going tonight and will do so into the future. The Simons Foundation just announced, by the way, fellowships, postdoctoral fellowship competition for people working at the boundaries between computation and theory and experimental neuroscience. And some of you should go out onto the website because it's a good opportunity. Academic jobs, I'm cautiously optimistic about because more and more people are realizing that the kinds of skills that you guys have, the kinds of quantitative perspectives that you have are more and more integral to making sense and understanding what the brain is about. We still have some problems in academia. Where are this new breed of quantitative neuroscience, where are they going to fit into traditional academic structures? And we're trying to sort that out, and I think far-looking academic institutions will get that sorted out. But for me as an academic, someone who really wants to see people studying the brain and trying to understand it, this is actually worrying. I mean, it's great for you guys, but it's worrying for me because so much of our greatest talent is being lured off into the private sector. And I don't know exactly what the future of that is, but maybe Google can become the Bell Labs of the future, which gave rise to so much great science. I mean, I don't know what that holds for us, but this is the paradox of the Ganguly brothers, right? One of them in academia and one of them building pipes in industry. So a bit of shameless advertising. There are jobs open at Stanford for people like you. If you go to the Stanford Neurosciences Institute, I'm the director of the Stanford Neurosciences Institute. If you go to our website, there are 5 open faculty positions right now that many of you would fit the profiles for, including a neuroengineering job, a theoretical computational neuroscience job, a broad area search in neurobiology, cognitive psychology, and electrical engineering that specifically calls out neuroengineering as one of the things that we're interested in. So all of you think hard about this and feel free to drop me emails and talk about this. But I'll close there and maybe we can go find drinks someplace else. Thank you.